Dear friends, in the last lecture we have discussed about the system view of processes and resources. In this lecture we will discuss some more aspects of process management. We will cover process address space, process abstraction, resource abstraction, process hierarchy and threads model in this lecture. First is process address space. Modern operating systems allow concurrent executions of multiple processes. One duty of the operating system is to protect each application process from interference by the others and to protect itself from them, so that a process cannot alter programs or data belonging to another process or to the kernel. The operating system solves this protection problem by implementing a concept called address space. Loosely, an address space consists of many different entities, for example, main function, function 1, function 2 up to function n, data etc., as shown in figure. These entities have distinct individual addresses in the address space. Address, which can be a name or a number, uniquely identifies an entity in the address space. An entity in the address space can only be referenced by using its address. For example, a collection of functions that are allowed to be executed by a process forms an address space. It is often called the logical or private address space of the process, and individual addresses are called logical addresses. When a process executes a program, it references entities in its private address space using the logical addresses of these entities as shown in this figure. Process uses logical addresses to specify addresses of the instructions and operands. Similarly, the operating system programs and data constitutes an address space called kernel space. Private address space of user processes collectively form what we call the user space as shown in this figure. Each application process is assigned a separate private address space which contains the programs and data that process can execute. Each process runs in its private address space and executes instructions and accesses data from that particular address space. It must not be able to interact with other processes or the kernel except through a set of communication primitives supported by the operating system. The system also has to ensure that a process confines to its activities to its own private address space. If a process tries to cross its address space boundary, the system intercepts the address space violation and takes appropriate action. As shown in this figure, address generated by a CPU called logical address is compared with base and limit registers to check whether the address belongs to the process address space or not. The execution of an application process alternates between the user space and the kernel space. The process primarily executes application programs in the user space. When it executes operating system programs, it is the kernel space and is considered to have effectively become a kernel process. In contrast, the original kernel processes always execute in the kernel space and never in the user space. When the operating system creates a new process, it initializes the process address space. In theory, an address space can be infinite. However, in practice, because of the limited availability of resources, address space are restricted to finite sizes. The structure of process address block has been shown in this figure. It contains 4 variable sized blocks: code, data, stack and heap. Next we have process abstraction. Process abstraction is a fundamental operating system mechanism for management of concurrent program execution. In reference to process abstraction, operating system perform many process management activities like creating and destroying processes, controlling the progress of the process, handling exceptional conditions arising during execution of a process, allocating hardware resources among processes, etc. User is not aware of all these activities. User thinks that there are multiple virtual CPUs for each of its program. The process of implementing user programs by converting them into processes and interleaved execution of multiple concurrent processes is called process abstraction. Process is a key operating system abstraction that users see. The environment you interact with when you use a computer is built up out of processes. The MS Word running on your computer generates process. When you execute a program you have just compiled, the operating system generates a process to run the program. Your web browser is a process. Video or audio players are processes. We may be running 5 or 6 windows of Internet Explorer simultaneously for surfing different types of data on internet, producing 5 or 6 processes. We never worry before opening new software or another copy of same software which is already running that how single CPU will serve so many applications. Operating system uses a context switch to switch from running one process to running another process. Operating system implements process abstraction to do this. Now, how to achieve this process abstraction? The processor executes programs of users sequentially or concurrently in an interleaved manner as shown in figure. In case of interleaved execution of programs, the processor executes parts of a program, parts of another program, parts of yet another program and so on and so forth until all program executions are complete. Actually, the processor executes only machine instructions sequentially, one instruction after another. It does not differentiate between the instructions of different programs. The processor executes instructions from the programs depending on the manner they are fed into the processor instruction execution stream. The operating system decides which instructions from which programs the processor would execute next. Although the processor executes one instruction after another of a certain program, the operating system may interleave executions of instructions from other programs. Then a definite need arises to supervise the various concurrent program executions to keep track of which program executions are using which resources, which of their instructions would be executed next by the processor, which program executions are initiated by which users, etc. Each program execution builds an execution context as the execution evolves. Program executions would behave correctly only under the respective execution contexts. The operating system tracks down program executions in the abstraction of processes. A process is an entity or object that represents a single computation and that models the execution context of the computation. Next, we are going to discuss resource abstraction. We have already discussed in previous lectures about resource abstraction. Resource abstraction is the process of hiding the details of how the hardware operates, making computer hardware relatively easy for an application programmer to use. Operating system implements resource abstraction by providing abstract interfaces with various resources as shown in figure. A separate device driver or controller is attached to disk, tape drive, memory, printer, etc. All these are resources to provide resource abstraction. Resource abstraction saves the programmer from need to learn about hardware details. Programmers need to be worried about their programming skills for solving particular tasks and not about how to interact with resources. Resource abstraction provides an abstract model of the operation of hardware components and generalizes hardware behavior. It hides the details of hardware by creating abstraction, allocate resources to processes. An operating system controls how processes may access resources and provide a pleasant and effective user interface. Next, we are going to discuss process hierarchy. In the programmer view, processes are a means to achieve concurrent execution of a program. The main process of a concurrent program creates child processes. In some systems, when a process creates another process, the parent and child continue to be associated in certain ways. The child can itself create more processes, forming a process hierarchy as shown in figure. The operating system initiates an execution of a program by creating a process for it. This is called the main process for the execution. The main process may create other processes which become its child processes. A child process may itself create other processes and so on. All these processes form a tree with the main process as its root. A process hierarchy in Unix operating system has been shown in this figure. A process has one parent but 0 or more children. A process, its children and further descendants together may form a process group. Child processes may communicate with each other. Accordingly, an operating system provides following operations to implement the programmer's view of processes. First is creating child processes and assigning them priorities. Second, terminating child processes. Third, determining the status of child processes. And last one is sharing, communication and synchronization between child processes. There are many advantages of creating child processes like computational speed up, higher priority for critical functions and protection of the parent process from malfunctioning of child processes. Lastly, we are going to discuss thread model. In traditional operating system, a process executes a single flow of instructions from its private address space called execution flow. At any point of time, the CPU executes at the most one machine instruction on behalf of the process. Until a process frees an acquired resource, it cannot be used by another process. Resources acquired by one process cannot be used by the other. This imposes a severe restriction on some high performance applications that need many concurrent activities in the same address space. Modern multi-threaded operating systems support multiple flows, also known as threads, in the application process. Thread is the smallest unit of CPU utilization. One process may have multiple threads and each threads make use of separate program counter, a stack of activation records and control block. However, address space, files and other resources are shared among sibling threads and parent processes. That is why a thread may also known as lightweight process, whereas parent process is called heavyweight process. The sharing makes CPU switching among peer threads inexpensive as compared to context switching among heavyweight processes. As shown in figure, multi-threaded applications have multiple threads within a single process, each having their own program counter, stack and a set of registers, but sharing common code, data and certain structures such as open files. But single thread application has exclusive control of all this. Traditional processes, also called heavyweight processes, have a single thread of control. There is one program counter and one sequence of instructions that can be carried out at any given time. A thread is a single sequential flow of execution of tasks of a process, as it is also known as a thread of execution or a thread of control. It acts as a mini process. Threads are the way by which a process is able to split itself into two or more simultaneously running tasks. In real life situations, it is possible that a program needs to perform multiple tasks at the same time. For example, in a word processor, a background thread may check spelling and grammar, while a foreground thread processes user input, while yet a third thread loads images from the hard drive as shown in figure. Threads operate same as processes in many aspects. Like process, threads may undergo a number of states during its life cycle. This is because in multi-threaded environment, when multiple threads are executing, only one thread can use the CPU at a time and other threads should be in some other state to be satisfied. As shown in figure, threads can be in one of the several states: ready, also known as runnable; not running state, also known as waiting, blocked or sleeping state; running state; dead state, also known as terminator state. Thread move among these states on the basis of various conditions as shown with arrow in this figure. Now, benefits of threads. There are few benefits of multi-threading. First is responsiveness. One thread may provide a rapid response while other threads are blocked or slow down doing intensive calculations. Second is resource sharing. By default, threads share common code, data and other resources which allow multiple tasks to be performed simultaneously in a single address space. Third is economy. Creating and managing threads and context switches between them, communication with each other is much faster than performing the same tasks for processes. Then we have various types of threads. There are two types of threads to be managed in a modern operating system: user threads and kernel threads. User threads are supported above the kernel without kernel support. These are the threads that application programmers would put into their programs. Kernel threads are supported within the kernel of the operating system itself. All modern operating systems support kernel level threads, allowing the kernel to perform multiple simultaneous tasks and to serve multiple kernel system calls simultaneously. In a specific implementation, the user threads must be mapped to kernel threads using one of the following strategies. First is many to one model. In the many to one model, many user level threads are all mapped onto a single kernel thread used on system that does not support kernel threads. One to one model. The one to one model creates a separate kernel thread to handle each user thread. Many to many model. The many to many model multiplexes any number of user threads onto an equal or smaller number of kernel threads, combining the best features of the one to one and many to one models. Finally, we have conclusions. The collection of all the logical addresses generated by a process during its execution is called process address space. A process during execution always refers to its address space for accessing the data and code. This makes possible the execution of multiple processes at same time. The existence of multiple processes and their independent execution hidden from user is called process abstraction. Resource abstraction is to hide the details of hardware from user. Creation of child processes by parent process is considered a process hierarchy. Threads are very important concept to improve the overall efficiency of the system. Threads are lightweight processes created by dividing a single process into multiple sub processes, each called thread. Thank you.